All right, so we have talked about all different kinds of regression, and now we need to talk about which type of regression should you use when it doesn't tell you. So our learning goals, we want to be able to compare linear, quadratic, cubic, and quartic regressions on a given set of data, decide which regression is best. Most importantly, we want to be able to mathematically and logically defend your choice of regression. So meaning we want to understand the reasons why you chose the type you chose. So a couple definitions that you're going to need in order to make this decision. The first one is coefficient of determination. This is the R squared that was on some of my screenshots, and some of you asked, I don't have that R squared, is that okay? And then it was. Today I'm going to make sure that you know how to get it on there because we will need it today. What it is it's called the coefficient of determination. It's used in statistics, and it's a measure of how well the model describes the data. R squared values are between 0 and 1, and the closer to 1 it is, the better your data fit the regression curve. Now, just because one R squared is closer to 1 than the other does not mean that that necessarily is the answer for the best regression. It's not the only factor you should consider. You should also consider validity, which by definition is the extent, for this instance, it's the extent to which the model corresponds accurately to the real world. So basically, this is asking, does the shape and end behavior make sense for real life? So if it's something that you know in real life is going to go up and then come down, you're not going to choose a model that goes to positive infinity on its right end behavior because that doesn't make sense for the real life data. Now, two other definitions that we're going to need to talk about are interpolation and extrapolation. Interpolation is when you are filling in data points between the data that you already have. So basically, I'm asking you for a value that is not listed in the table, but it's within the X range of the data you already have. Extrapolation, in contrast, is when you're filling in data points that are beyond the data that you already have. So you're basically extending it and using it for prediction is what extrapolation does. It uses the data for prediction, which technically you should really not do, but people do it all the time because we have to have something to use to predict what's going to happen. So we're going to look at this problem. A projectile is fired upward from the ground. The height of the projectile above the ground is shown in the following table. Find a good model to fit the data. So first thing we're going to note is that the time data, which is our x, is evenly spaced. So we might be able to have finite differences help us. Now again, finite differences could only possibly help if the x data is evenly spaced. So we can go ahead and try it. You know how to do finite differences, so go ahead and pause it and do your finite differences, then unpause to check it with mine. Remember, it's always right minus left, so 20.5 minus 0, 31.36 minus 20.5, so on and so forth. So go ahead and pause it and then come back to see if you've got it right. So I'm using a calculator for all of these here because of the decimal points. It's just easier to make sure that you don't make a silly, careless error. So my first order differences are up there. And those are definitely not constant. So I go on to my second order differences. And here I've got negative 9.64. Then negative 5.97, negative 10.73. It's kind of hard to read, sorry about that. 3.66. Looking for third order, because second order aren't constant either. And that gives me 3.67 and negative 4.76 and 14.39. So third order differences don't work. Fourth order differences, I can already see that they're not going to be the same. So here, this is like so maddening because we just spent all this time doing the finite differences and it didn't help us because the finite differences were not constant even in our fourth order. So finite differences here didn't help. So no help on this one. But again, sometimes it will. So you want to check it because that is one of the things you can use to make your argument for which type of regression you want to use. So now we're going to use the calculator and we're going to check each of the regressions and report our R-squared values. So again, R-squared isn't the only determining factor, but we want to look at it all. Now, this is very important for those of you who didn't have R-squared on there. This is what you press to make sure that R-squared shows up with each of your pieces. You press second, then you press the 0 button, so the actual number 0, because above that in the second button color is the word catalog. And when you do that, it brings up a whole alphabetized menu, so you want to scroll all the way down until you see diagnostic on. So make sure your little triangle is on diagnostic on, and then press enter. That's going to make sure that your R-squared value appears. Next, we want to make sure that our plot is turned on, so make sure that your plot is on, clear anything that's in your y equals, we don't want that. And then we want to go ahead and clear your list 1 and list 2, so stat, choice 4, clear list 1, comma, list 2, press enter, and then go ahead and enter your data. So in L1, we're going to have the time, so starting with 0, and then 0.5, 1, 1.5, 2, and 2.5. Then our L2 is going to be the height data, so the 0, the 20.5, so on and so forth. So please enter all of that data in your L2. Make sure it matches up, double check the data. There's not that many data points, but having the wrong data points will just mess everything up. So what we're going to do is we're going to do one regression at a time, and we are going to paste the regression equations and sketch them. This is not, you are not actually scatter plotting. This is a rough sketch of the scatter plot. Notice that I've told you here what to use for your windows, but you could probably come up with that on your own as well. So on the X, we're going to go well above what we need. We're going to go from 0 to 10. On the Y, we're going to go from negative 10 because we always want it to be below the axis on the Y. And then we're going to go up to 50. So we could probably count by 5s maybe there. So we are going to do the linear model first, so that means we are going to press Stat, Calc, and we're going to choose choice 4, linear regression. Now, if you have the older model, you're going to be typing in L1, comma, L2, comma, don't forget to do the Y1. We want to paste the linear model in there so that we can look at it. If you have the newer model, then you scroll down to where it says store regression equation, and you put in your Y1. So press enter or press calculate, and our linear model is y equals, it says round to 3 significant figures. So remember, that's not 3 decimal points. So here's 1, 2, 3 significant figures, and that's x. So 10x essentially plus 11.9 would be 3 significant figures. Our R-squared value, you can see it displayed there if you went through this up above like I instructed. So I'm going to round to 3 significant figures here. Remember, the 0 before the decimal point is not significant, so 0.519. Now, I will tell you that even if it says to round to 3 significant figures, sometimes on R-squared, you're going to have to go past that to see a difference. So if that's the case on R-squared, you can ignore this when necessary. So now I'm going to look at my graph, and I'm just going to do a rough sketch. So the points that I've got look something like this, and my linear model looks something like this. So it doesn't look like a great model. R squared indicates that it's not real close to 1. So now I'm going to look at the quadratic model. So that means I can go to Stat, Calc, and choose choice 5. Again, unless you want to keep the line, which you can if you want, you're going to do the exact same thing with the quadratic that you did with linear, L1, L2, Y1, which will repaste the quadratic model in Y1. If you want to keep it, then maybe you want to put the quadratic in Y2. But unless you're having problems, there's really no reason why you might want to keep it. So the quadratic model, A is negative 12.87, so to 3 significant digits, that's negative 12.9, that's x squared. My B, 42.2x, and my C, 1.1, approximately 8. So there's my quadratic model. My R squared here, much, much better, 0.974. And when I look at the graph, again, the data points should look relatively the same, but the model should look different. So it's going through almost all of them, and it looks like that. So now I'm going to try the cubic model. So Stat, Calc, choice 6 now for the cubic. Again, you can store the regression equation on top. So on the cubic, I'm going to store that and calculate. So my A is 3.868, so that's 87, that's x cubed. My B value, negative 27.4, x squared. My x coefficient is positive, so plus 55.5x. And then my constant is negative 0.273. So there is my cubic model. My R squared here is 0.992. And when I look at the graph, again, the data points really should be in similar places. Again, this is a rough sketch, so you're not actually plotting them. And the cubic model kind of goes like this. All right, quartic model. Stat, Calc, choice 7. So we're just going right down the list, storing the regression equation each time as we go. And here my A is 3.573, so 3.57 will work, and that's x to the 4th. B is negative 13.99, so we'll make that 14.0, x cubed. Then my C value is very small, it's 0.061, that's x squared. My X is 42.7, and my constant is 0.109. Now notice here, because the entire screen is taken up by the coefficients of the model, that you actually have to scroll down to see your R squared. So R squared here is 0.996. We look at the graph, and again, it almost looks like the cubic. It looks very, very similar. Very hard to tell the difference between the cubic and quartic model. So now we need to make a decision. So finite differences didn't help us. The R squared, we have 3 values that are above 0.9. The quadratic, the cubic, and the quartic are all excellent R squared values. So that means we're not just going to base it on R squared, we need to think about the validity. So what is this situation representing? It's representing a projectile that's being fired up from the ground. So when you fire something up from the ground, it goes up, but then what should it do? It should come down and keep coming down. And the only model that does that is the quadratic. The quartic and cubic, if we extend the data, the end behavior is going up over here. And projectiles, once they start coming back down, they don't go back up because it's not powered. It's not like a plane that can do that. It's fired and it's going up and then gravity brings it down. So the regression model that I am going to choose here is the quadratic. I'm going to say that the quadratic is best because the projectile should come down and stay down. And the quadratic is the only model with that end behavior. All right, so now that we've chosen our model, now we can answer some questions about it. So we're just going to ask one question. So you need to go back to your y equals, clear out the quartic equation, go back to your stat calc, and you want to paste the quadratic regression back in your y1 because it's the one that we chose. And you want to graph it because now it wants to know when the projectile hit the ground. So in order to find that, we just need to find the second zero, which we've done plenty of times when we studied quadratics and when we did our polynomials. So we will graph it, and then we are going to do second trace, choice 2, which is find the zero, because we want to find this right here. That's where it hits the ground. So second trace, choice 2. Remember, left bound, right bound. You can look at the bottom to see where the y values are, but left bound is going to be over here. Left bound is over here. So press enter. Then right bound, make sure you dip below the axis for right bound. Press enter and then tell it to guess. And it is telling us that the x value there, the time, is when x is 3.3, and since we're rounding to 3 significant figures, we'll say 3.1, and that would be in seconds. So to summarize your general guidelines, check the finite differences if the data is evenly spaced. It's not always going to help, but if it is, that would be a big help. Always, always use quadratic for projectiles and falling objects because that's how gravity works and projectiles. So if it's something that's falling or being thrown and then falling down, always use quadratic. But if you have lots of decent r-squareds, you generally want to use the lowest degree possible, which we did here with the quadratic. That's if you're interpolating. If you're extrapolating, meaning using to predict the future, you want to make sure you focus on the end behavior, what's valid for the model over time. So once you've considered all those things, you choose your model, you have to. The most important part is, can you defend your choice? Why is it the best model? And that's it for today.